Yo, 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 algebra students, 10-4, inverse of a function, pot 3, horizontal line test. Oh my gosh, remember the vertical line test? Now we have a horizontal line test? Let me explain why. Okay, below is the parent graph of a quadratic function, f of x equals x squared. We know that 0 squared is 0, 1 squared is 1, 2 squared is 4, negative 1 squared is 1, negative 2 squared is 4. Okay, so far so good. The inverse of this function can be found by switching the inputs and outputs of the ordered pair solutions. So f of x has the following ordered pairs. Negative 2, 4, yep, negative 2 squared is, quantity squared is 4, negative 1 quantity squared is 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So the inverse of the function will switch the inputs and outputs to get the following ordered pairs. So instead of negative 2, 4, right, now it's going to be 4, negative 2. That's supposed to be a negative. Okay, and then negative 1, 1 is going to become 1, negative 1. 0, 0 will stay 0, 0, because when you switch it, it's the same. Same thing with 1 and 1. And then 2 and 4 becomes 4, 2. Okay, so now let's go ahead and graph. Below is the graph of the inverse of f of x equals x squared. If I just graphed all these points, 4, negative 2, 4, 2, 1, negative 1, 1, negative 1, 1, 1, 1, 1, and 0, 0, I'm going to get this graph. Now, compare these. Do you see something about the inverse of f of x equals x squared? It looks like the original graph on its side. Okay, now, is this a function? And while I was putting those points on here or showing you where they are, hopefully you saw, no, if I had a vertical line, right, passing through this function, how many points would it hit? It would hit 2, right? For a lot of the domain, it would hit 2. That means at an input of 4, I have 2 outputs. Notice that this is not a function because it doesn't pass the vertical line test. So the inverse of something that is a function, this is a function, right? Passes the vertical line test, but its inverse is not. So there are 2 outputs for 1 input. So not a function. That's supposed to be a U. Oh, I can fix it, kind of. All right. Notice too that the graph looks like a parabola on its side. Before we found the inverse, we could have drawn a blank line. Now, wait a second. What kind of line? This passes the vertical line test, but if this is going to end up being on its side when we get the inverse, couldn't we have drawn a horizontal line? If we had drawn a horizontal line, what would that have told us? It wouldn't have told us whether this is a function. This is, it passes the vertical line test. But if this function's graph doesn't pass the horizontal line test, that means its inverse won't pass the vertical line test, so it won't be a function. Before we found the inverse, we could have drawn a horizontal line to check if the graph of the inverse would be a function because it would pass the vertical line test. That's supposed to be a C. So if we use this horizontal line test on any function, this is a function, right? F of x equals x squared is a function. But if we had checked the horizontal with the horizontal line test and went, oh, it fails, that means its inverse would not pass the vertical line test, and therefore the inverse wouldn't be a function. The original function, definitely a function. Its inverse, not a function. Let's go into more detail about why this happened. It's a little strange and it takes a little getting used to. And the way that we're going to fix this situation where the inverse is not a function is we're going to use the principle of restricting the domain. Okay, so this is going to be kind of complicated, but once again, you can do it. Restricting the domain. Let's go back to the last example, f of x equals x squared. What if we restricted the domain so that the graph would pass the horizontal line test? Here's how we can do this. Okay, f of x equals x squared. That's the original function we just had. Remember, it makes the parabola. But this semicolon is going to tell us where the domain of this function is going to be graphed. and the domain is when x is greater than or equal to 0. So you would read this as f of x is equal to x squared when x is when that semicolon, when x is greater than or equal to 0. The most important part is that the semicolon means the word when. So we're only going to graph this function, or we're only going to use solutions when x is greater than 0. Okay, now let's find the inverse algebraically. So f of x becomes y, so y is equal to x squared. Switch the input and the output, so x is equal to y squared, and then solve for y. To solve for y, you take the square root of both sides, you get y is equal to the square root of x. That's interesting, because when we take the square root of a number, do we usually take the positive or the negative root? Just the positive. So that's going to be important. There are a couple important points here. First, when we take the square root of a number, we only take the positive root, not the negative root. Not the negative root. This is called the principal. Whoa, that's spelled wrong. Might have been autocorrect. Principal square root, which is the positive one. Why does this make sense? Well, let's go back to the original equation. F of x is equal to x squared when x is greater than or equal to 0. Let's write some ordered pair solutions. 0, 0, 1, 1, 2, 4, 3, 9. Now you may be wondering, well, what happened to negative 2, 4 or negative 1, 1, like we had in the example before this? Notice that we had to get rid of the solutions such as negative 2, 4, negative 1, 1, because the domain is restricted. Remember, x has to be greater than or equal to 0. These x's are not greater than or equal to 0. So that's good, because now the inverse can be found, but switching the, let's say by, sorry about the typos, everybody. I'm trying to do too much today. By switching the inputs and outputs of our ordered pairs, and we'll notice that we don't get any negative outputs. Oh wait, no, maybe that is supposed to be but. I apologize, I don't even know what I'm doing anymore. Here's the main idea. If we only take these solutions, right, where x is greater than or equal to 0, and we switch the inputs and the outputs, 0, 0 stays the same, 1, 1 stays the same, 2, 4 becomes 4, 2, 3, 9 becomes 9, 3. In other words, just like only taking the principal square root in the function y equals square root of x, we never get the same input giving two outputs. So notice, the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. What kind of outputs are we not getting? Negative outputs, because we shouldn't when we only take the principal square root. So by restricting the domain on the original function, we are actually setting it up to be its inverse with a square root, where we're only taking the positive root, the principal square root. Let's take a look at what the graphs look like, and that'll help illustrate this even further. So let's look at the graph of f of x equals x squared when x is greater than or equal to 0. Well, this is what the graph of f of x is equal to x squared looks like. But what part are we going to get rid of? We're going to get rid of this red part. Why? Because this side of the graph is x is less than 0. We only want the side of the graph where x is greater than or equal to 0, which is the purple half of our graph. Now notice the red half of the graph is not going to be there when we restrict the domain, because we should only see points where x is greater than or equal to 0. Without the red half of the graph, this would pass the horizontal line test. If this red half is gone, whereas before it would have failed the horizontal line test, now it'll pass because this side has been removed by restricting the domain. So now let's take a look at what the inverse would look like. Let's say we didn't restrict the domain. Notice there's the red half of the data right there, but it's gone now because we have restricted the domain in the original function. So this red part is going to be gone. Remember, the red portion of the inverse is now gone because we restrict the domain. So the graph of the inverse looks like this purple line. This purple line without the red part So the original function, f of x is equal to x squared when x is greater than or equal to 0, with the restricted domain, passed the horizontal line test. So we know the inverse would pass, or we knew the inverse would pass the vertical line test. And as you can see, it does. If I draw a vertical line anywhere along this whole graph, it'll pass the vertical line test. The same as the original function passed the horizontal line test. You can sometimes blank the domain so that the function passes the horizontal line test. You can sometimes restrict the domain. You can restrict the domain so that its inverse will pass the vertical line test. So you restrict the domain of the original function, it passes the horizontal line test, and then its inverse will pass the vertical line test and continue to be a function. All right, that's it. You are all amazing students. Thank you so much for watching these videos. I know this is tough. Of course, if I can answer any questions, let me know. You're great people. Keep up the good work.